Alright everybody, we're going to go over the Thermochem Postlab. Many of the calculations you see here will be very relevant for the exam. And where we're going to start off first is part 1, where we're looking at the data that you should have collected. Okay, so here's your sample data. You should have the mass of cool water. Here's just a sample number. You should have the mass of the hot water, around 30 grams in this example. The initial temperature of the boiling water better be around 100. And then you have the initial temperature of the cool water, that's somewhere around room temperature. And then you should have the highest temperature reached. So you mix these two, you should have a number in between them. We're going to use all of these numbers to do some calculations. To solve this kind of problem, any sort of heat problem, you use the law of conservation of energy. The sum of the Q's equals 0. So you need to figure out what Q's you have, and you're going to set that equal to 0. So basically, what changes temperature? So in this problem, we have several things. The hot water, I'll put Q hot. That one's decreasing in temperature. Then you also have some cool water, Q cool. That one's increasing in temperature. And then finally, you also have the calorimeter, your cup. So I'll write cal for calorimeter. That is also warming up. So those are the three things that you're going to have in there. Now you need to set, okay, so let's break down all three of these. For Q hot, really all the formulas are going to be the same. They're going to be M, C, SP, delta T. Okay, all three formulas will be the same thing. This mass is going to be the mass of the hot water, which we just collected and just told you about. It's 30 in our case. You're going to have CSP, that's for water. And then you're going to have the delta T. So that'll be T final minus T initial for the hot water. Okay, so it'll be the T final in our case will be 40, and the T initial for the hot water will be right at 100. And then let's take a look at the other ones. Q cool. Really similar, M, C, S, P, delta T. What's the difference? Not too much. It's just going to be the mass of the cool water in this case. All right, cool here by mass. We still got water, so I'll put a W by the CSP. And then the T is going to be, it always ends with T final. So the T final is the first number you write, but the T initial in this case is of the cool. So T final minus T initial of the cool. And then the calorimeter, right here, and this contains the variable for which we're going to solve. This is CP. Remember, CP is M times CSP, but we only need CP for our calculation. So this is going to be CP for the calorimeter times a delta T. So just like before, the delta T, let me write that out. Remember, the first number is always going to be the final, and there'll be T initial, in this case of the cool water. Because the calorimeter and the temperature of the cool water will be the same. So you're going to use the same number right there. First one, the heat lost by the hot water. And this will be the same kind of pattern or flow that you'll see in your post lab. That's Q hot. We saw that over here. It's going to be M CSP times delta T. But let me plug in the numbers just so you know what everything is. So the mass for the water, that's going to be 30 grams. And then we're going to put the CSP for water, that's 4.184 joules per gram degrees C. And then finally we're going to do the temperature difference. The temperature difference is T final minus T initial for the hot. T final is 40 and T initial was 100. Meaning T final was 40 degrees. That was the same T final for everything. T initial is the temperature of the boiling water, which is 100. Okay, now let's look at the second one. The second one goes like this. It's Q of the cool water. And that's the one right here, MCSP delta T. So we're going to use that formula. The mass of the cool water we found from our data, or had from our data, that was 70 grams. 4.184 joules per gram degree C for CSP. So that's as before, that's a constant. And then we've got T final minus T initial. T final in this case is 40, but the T initial of the cool water is 25 degrees. So let me write the answers in this example so you can see if you got the same calculation. This one, the first one in our case is negative 7531.2 joules. If you calculate Q cool, you should get positive 4393.2. So you can see that Q loss should be a negative number, and you should say that Q gained or heat gained should be a positive number. Okay, Q cal for the calorimeter, we need to solve this equation before. So if we move Q cool and Q hot over, we get this equation, solving from the original energy balance. And then now we just plug in our numbers. So this is negative. For Q cool, we just solved that. That is 4393.2 joules. And then we add Q hot, we also just solved for that. That's negative 7531.2. So make sure you get your signs right. 7531.2 joules. And this will be Q of the calorimeter. You better make sure you have your signs all correct. And I got 2958.0 joules. So there's Q cal. The last step is find the heat capacity of the calorimeter. This is what we're going to use throughout the rest of the calculation. Remember, if I rewrite that formula, Q cal equals C, really CP of the calorimeter times delta T. Okay, Q cal we just found. That was 2958.0. CP is what we want to know. Delta T, let's find that. T final was 40. T initial, because the calorimeter is touching the cool water, is the same temperature initial of the cool water, which was 25 degrees C. You have to solve for CP. It's going to be 2958 divided by 40 minus 25. And that's going to turn out to be, in our case, 197 joules per degree C. That's what we got. This better be a positive number or something has gone wonky when you've done the calculation. And we're done with part one.